what the ICM325A head pressure control is, why we need it, and how it kind of works, and very general in the sense of how it works, just give you an overview of how it works. And then we're going to get into the wiring, because a lot of techs have a lot of sometimes have trouble with wiring, and so we'll talk about the wiring a little bit, and we'll go into a little bit more detail on that so that we all understand what the control does, why you need it, what's the good selling points about it, and then how to wire it, how to properly set it up with the app. And a little bit, we'll go over a little bit of what's different about this model versus maybe the older traditional model without the app. So, okay. So what are low ambient head pressure controls? Low ambient head pressure controls are basically electronic speed controllers for your fan. They use temperature probes or pressure transducers that sense the condenser temperature or pressure in the systems and vary the output power to the condenser fan motor to slow or speed up the fan motor. And by doing this, we can control how much air is going past the condenser coil, which then will maintain our head pressure in very low temperatures. Now, we'll get into why that's important in the next few slides. But I like to compare this to a dimmer switch. In short, these are very much like a dimmer switch in your house. So in your house, you have a dimmer switch on the wall. You adjust the resistance of that little dimmer switch potentiometer, and that changes the output voltage to the light bulb. Well, in a very similar way, when you use the temperature probe, that changes resistance according to the temperature of the condenser coil, and that changes the output voltage to the fan motor. So it's a dynamic, automatically controlled, so to speak, dimmer switch. And pressure transducers are no different. They just sense the pressure directly and send a little signal back to the ICM control to adjust the output voltage to the motor. So a glorified dimmer switch is a great way to get a general sense of how this thing works. By adjusting the amount of airflow we push past the coil of the condenser, we can maintain and control our head pressure much better than the rapid swings of fan cycling type controls. All right, so why are head pressure controls needed? Why do we need these in the industry? Well, air conditioning systems and refrigeration systems are commonly required to operate during these low temperature conditions outside. We have to have food cases, refrigerator cases. We have to have our cell towers cooled down. A lot of equipment in that cell tower gets very hot. So no matter how cold it is outside, we still have to have air conditioning to cool equipment. So operating cooling in cold weather conditions causes the system head pressure to drop. So pressure and temperature are directly proportional. So as the temperature outside decreases, the pressure in your system also decreases. It can get low enough where you can get to the point where it's damaging to your equipment. You can have low pressure cutouts, evaporator freeze-ups, liquid slugging of the refrigerant, compressor burnout, and erratic fan cycling if you don't have head pressure controls like the ICM325A. So the solution is install an ICM325A head pressure control to control that fan speed. So low ambient control applications. Well, we see these all over the place, right? Manufacturing plants, server rooms, frozen food storage. All these places need low ambient control to maintain their AC units even during very cold weather outside. Frozen food storage, heat pumps, grocery stores and supermarkets, they have freezer cases. All this stuff needs it. Medical offices, event spaces, you get a lot of people in one room, you still need air conditioning. Temperature and humidity sensitive environments. We're seeing new opportunities now in grow houses and cooling towers as well. So what makes the ICM325A superior to other types of head pressure control out on the market? Well, one of the big things is the universal function of our control versus some of the other controls that are out there. Ours can replace literally all of the legacy ICM control head pressure controls we had before. So this is a one part fits all to all our past head pressure controls, which had different SKUs for different voltages and different reversing valve operation. Now all of that is combined into one universal control, which makes it really nice for our distributors and our customers. You got a one-stop shop for your head pressure control. Universal input voltage, reversing valve voltage, control voltage allows you to use this one control rather than having many separate SKUs. It also accepts up to 2 pressure transducers or 2 temperature probes so that you can, if you have a unit that has multiple condensers but 1 fan, you can monitor both of those condensers, and the control has internal logic that will pick the unit with the highest pressure and control the fan based on that unit. Some people have even used these, and when they got coils that are in that they've got several loops in the coil, they can put one on one loop and one sensor on another loop, and they can get better head pressure control that way as well. So it's a perfect one item fits all for your single phase PSC head pressure control needs. And don't forget, it has the ability to operate 2 condenser fan motors up to a 10 amp limit. So that's another question a lot of people ask when they call in technical support is that, hey, can I run 2 fans off of this? Yes, you can. As long as you keep the commons of both of those fans in parallel with the motor 2 output, then yes, we will control both of those fans at whatever speed the pressure sensor or transducer is telling it to do so. So let's look at variable speed versus fan cycling. So why would you want the ICM325A that is variable speed versus just a typical cheap old fan cycling control? Well, variable speed now stabilizes your head pressure and reduces wide swings in the pressure. That's completely unacceptable. Wide swings in pressure are completely unacceptable in grow houses and places like that, where you need to maintain a more consistent temperature overall. Smoother operation reduces rattling of pipes and ductwork, preventing leaks. This increases the lifespan of the condenser, fan motor, and compressor, eliminates a lot of those callbacks for leaks, refrigerant leaks, and so forth. It also eliminates the constant on-off torques on the fan blade and compressor that prevent costly repairs. And you maintain an overall more even cooling, which is exactly what you're going to want in a lot of these applications. So the value-added features of the ICM325A specifically is it carries near-field communication technology. Now you say, well, what's that? Well, if you've ever used Apple Pay with your Apple Watch, that's near-field communication. It's basically, there's an antenna inside the ICM, and there's an antenna in your phone. And you take your smartphone, you download an app, and then the antenna in your phone communicates the information from the app into the antenna that's in the ICM and programs the ICM. So it's a way to program the ICM and set it up without the use of the internet or any Wi-Fi. So there's no Wi-Fi. If you don't have a Wi-Fi network available, you're out in the boonies somewhere, not a problem. Near field communication doesn't require that. It also makes it convenient for people that want to set the control up prior to going up on a windy, cold roof. They can set the control up right in their truck, in the warmth of their truck, with the near field communication. They can program several controls if they have more than one control to install, and these will this near field communication will make that possible. So the other thing, it's very quick and easy to support. So if you ever have any problems, all you gotta do is just call ICM Controls Technical Support and we'll help you through setting it up. It's very, very easy, very few steps. And we'll go over those steps, later on in this presentation. The other added value is that it's designed and assembled in the USA. That makes a big difference because it makes it more reliable with the quality, superior accuracy and durability of the design, but also keep in mind, since we're molding our own plastics and we're designing and producing all of our own parts, it makes it a lot easier to produce and available to the distributor. So you don't have to wait, for other things. Shipments overseas, tariffs and all that stuff can prevent a lot of things from happening, where if it's designed and manufactured here, it supports our own local economy and it's easy to put on customer shelves, on distributor shelves, and support production. All right, so the universal parts advantage for distributors is that you're going to get a quality product, reduce your inventory, more turns basically in your inventory, so it'll reduce your amount of inventory, and you can turn product much more quicker because you're not waiting for shipments to come in. We're building them at the factory. We can ship them direct right to the distributors in a very quick manner. Single U.S. source, so you don't have to worry about, oh, is this boat held up here? Is this shipment held up there? Oh, do they have a shortage of parts due to tariffs? And so forth. All done here, so we can meet those distributors and manufacturers' needs. They're highly manufacturable because we mold our own plastics and we place the electronic components on our own circuit boards, and we build the product all here in our state-of-the-art vertically integrated facility. And it's a versatile on-hand solution for the distributors. So you can easily get parts, you can reduce your inventory, you're going to get a quality product that's easy to manufacture and easy to supply to our distributors. For the contractors, it's a quality product again, but you're going to reduce also your truck stock. You don't have to now have multiple SKUs for the same product. All right. You can reduce your trips back and forth to the distributor because you've got universal input voltage, universal reversing valve inputs, universal control voltage. So you don't have to worry about, the refrigeration guys don't have to worry about picking a special unit that's only for line voltage reversing valves. It's all universal now. So now it makes it much easier for contractors to pick one product, put it on their truck, less back and forth trips, makes the repair time a lot quicker. You can program these things in your truck. You don't have to worry about timely setup. So it can be done ahead of the job. Just go into the job, wire it up and take off, because now you've got that pre-program available to you with NFC technology. They're easily available, easy to install, and competitively priced. So contractors are going to really like that. All right. So those are the advantages of why the ICM, you would choose the ICM, and why we need them. Okay. Now let's talk a little bit about the problem that usually people have is, how do I wire this thing? What is it doing? Well, let's just look at this. We can look at this diagram, and we can break this diagram down into a very simple conclusion. Basically, what you have to do is you have to supply power to the ICM. That comes from the load side of your contactor. Now, this is a typical HVAC air conditioning application. This is not a heat pump in this example. We'll show you a heat pump in a moment. This is your typical AC. So you got a contactor that turns on your fan motor. That contactor supplies voltage, 240 volts, let's say, to your fan motor. What you've got to do is you've got to supply that same voltage to the ICM at line 1 and line 2. And then simply, we're gonna break that line 2 that would have went back to your motor. We're gonna break that through the control at line 2 to motor 2. So just like your dimmer switch in your house has power going into the switch, then power coming out of the switch and going to your light bulb, it's very much the same here. Power is coming into the contactor, going out of the contactor through the ICM, which is like your dimmer switch, out to the motor, which is like your light bulb. And all we're doing is we're just breaking one leg of that power through the ICM so we can control the voltage going to the motor. So you see line 1 simply connects to the common of the capacitor, which then not all of these are going to have a single permanent split capacitor fan motor. So you're going to have this capacitor. It'll either be a dual run capacitor like you see here, or you might see a standard star capacitor, but most of the time you're going to see a dual run capacitor like you see here. So the HERM is just going out to the compressor. All we're really concerned about is the 2 terminals for the common of the fan. Now, line 1, the dashed line represents a field installed wire that goes to the common of the capacitor. So we're just picking up T1 power from the contactor. So T1 is just the load side of the contactor opposite of line 1. When the contactor pulls in, that T1 power powers the common of the capacitor, also powers line 1 of our control. T2 normally would have gone back to the common of the motor. It would have just went to the other side of the motor. However, we're going to take T2, we're going to take that black wire off the motor, that common of that wire off the motor, off the contactor, sorry, not off the motor, off the contactor, and we're going to just bring that wire to line 2 of the ICM. So now you've got a direct connection from the other side of the line to line 2 of the ICM. That's your 240 volts. Now, you'll still have that wire from the motor in your hand. That's just going to go to motor 2. So it's literally just 3 wires there. You got the one side of power to the motor, which I'm calling the common of the motor, that's going to motor 2. You've got T2, which is one side of your main power from the contactor going to line 2. And T1 coming from the common of the capacitor going to line 1 of the ICM. So it's literally just line 1 and line 2, and you're just breaking that leg of power that would have normally went from line 2 back to the motor. You're just breaking that leg of power through the ICM and connecting the motor side to motor 2 and the line side to line 2. And then the other 2 connections are just simply the temperature sensor, which go to T1, P1 and plus 5 volts. Please do not confuse it like many people do and put the sensor across T1 and T2. It doesn't go that way. You have to supply voltage to one side of the sensor. So plus 5 volts on one side of the sensor, and that's the temperature sensor, and then T1, P1 for the other side of the sensor. All right. And the pressure transducer will also have a wiring diagram on the installation guide. So the next diagram will show you how we do the same thing, only it's a little bit different wiring when it comes to heat pumps. All right. Now, when we talk about heat pumps, remember heat pumps got a defrost board, and a defrost board needs to be able to shut off that fan motor when you go into the defrost cycle, but yet bypass the ICM control when it wants to be in heat mode. So with a defrost board, we have to accommodate for 2 things. We have to accommodate for when the unit goes into the heat mode and we want to bypass our control. And we also have to accommodate for the defrost board when it wants to shut the fan off during the defrost cycle. We only want our control to be in play during the cooling mode. So this is why we can't go directly from motor 2 back to the motor like we did before. What we have to do is we have to, instead of taking the motor wire off the contactor, now we've got to look at the relay that's on the defrost board. So the defrost board is going to have a fan relay that powers the fan. we're going to look at the power going into that relay. Okay? And we're going to take that power that goes from the contactor into that relay at the COM terminal of the relay, or sometimes they're labeled ODF, outdoor fan 1, or DF1. Whatever that power is coming from the contactor to power that fan relay, we're going to take that power off and we're going to put it to line 2 of the ICM. All right. So the contactor again goes from T2 to line 2 of the ICM. Now we're going to make our own field installed wire, and we're going to go from motor 2 of the ICM back to that DF1 terminal on the fan relay. In this case, it's called common on the fan relay, but a lot of defrost boards that might be labeled DF1, DF2, ODF1, but you're going to see a power leg. So that power leg has to be powered by our ICM control, so that when we are in cooling mode, we are modulating the voltage through that relay to the fan mode. Okay, all the other connections are exactly the same. The only other connection that you have to be concerned with is the HPORV jumper and the reversing valve input, HPRV input. So on a heat pump, you have a reversing valve. Now that reversing valve it can be either heat active or it can be cool active. Now our device is preset for heat active reversing valves. So a lot of your typical heat pumps are cool active. So with cool active reversing valves, what you're going to do is just simply put a jumper at HPORV, which O stands for the cooling active reversing valve. That's going to condition the input at the HPRV to say that when we see a voltage there, we know that we're in cooling mode and we can go into variable speed mode. But when we don't see a voltage there, we know we're in heating mode and we will bypass this control and run the fan at full speed. Okay? Because you never, in a heat pump, when you're in heating mode, you always want the fan at full speed. And so that's all we're looking at on the HPRV input is we're looking at the input of the reversing valve, whether it's going to be heat active or cool active. So that's, you're paralleling 24 volts off of the defrost board to that HPRV input. Okay, so it's either going to be 24 or 240 if it's a line voltage reversing valve. You're just paralleling that voltage off of your defrost board, and then you're choosing which direction you need to go. If you have a cool active reversing valve, you have to place a jumper at HPORV. If you do not have a cool active reversing valve, if it's a heat active reversing valve, you need no jumper there. Control voltage on this control is optional, so you don't need to wire that in. So in this case, you have the 3 wires up at the top, you have the 2 wires for the sensor, and you have an additional 2 wires for the reversing valve. So this one would be a 7-wire application, 5 wires for the standard wiring and 7 wire for this product with the heat pump. So once you get everything wired up, she starts up. If everything goes well, then the control will sense what the pressure is and or the temperature, and it'll say, okay, it might wait a few seconds for the pressure to build up to a certain range where it needs to turn on the fan. Because remember, when the control senses it doesn't need the fan, it'll keep that fan off. When it does need the fan, it'll turn it on either in full speed if it needs it, or in variable speed if it should be in variable. So what it does is you turn on the unit, maybe it takes a couple of seconds to build pressure, then the fan will come on at full speed for a very short hard start session, maybe a second or two, depending on how you have your hard start setting. And then it will see, okay, where is my pressure? Okay, if it says, hey, I need to slow this fan because my pressure is not high enough, then it will slow the speed down and build that pressure up and try to maintain that pressure that you have on your set point within plus or minus 15, 20 psi. Okay, so it's going to ramp up and slow down, ramp up and slow down, and try to constantly maintain an even head pressure. If it doesn't do that, if something is wrong, then it's going to flash you a code. So if both of these lights are off, it means you have no voltage at line 1 or line 2. If both of those lights are off, it also could mean you have no control voltage when you have the control voltage input selected. Or it means that simply the output is off. It's just not ready to turn on yet because your pressure in your system is too low. Now, if you have the green light on, but the amber light off, it just means you're in full speed operation. If you have the green light off, but the amber light on, it means you're in variable speed operation. And we denote that by the words that are printed right on the controller. Now, if your green light is off, but you get a 2 flash code on the amber light, it means you have a shorted sensor input. And if you have the green light off and you have 3 flashes on the amber LED, that means you have an open sensor. Your sensor's not working. So we can kind of give you some indication of how this thing is working and a little bit of troubleshooting feedback for the technicians. All right. Now, near field communication. Talk a little bit about that. So ICM Controls leverages NFC technology so installers can adjust their settings using a mobile device. Now, this will work with both Android and Apple devices, all right? And NFC is a short-range wireless technology. It doesn't mean it's internet. It doesn't mean it's Wi-Fi. It doesn't mean it's Bluetooth. It's none of those things. It's a short-range wireless technology that allows your phone to act as a transit pass or basically a quick transfer mechanism to instantly pair with your ICM325A. I'm not sure why this says the Bluetooth devices. That was from a previous presentation, so I'm sorry about that. You can strike that off of there, but basically it's as I explained before, it is a type of communication that uses the antenna in your phone to pair with your antenna that's in your ICM325A using the principle of induction. No wireless connection, no Bluetooth connection, none of that. Just a field that's generated by your antenna on your phone to a field antenna that's in the ICM, and they just information transfers that way. No pairing is necessary. It eliminates the need for costly displays on the appliance, which keeps our price point down. It enables quick customization of the device settings. You can save programs so that you can program multiple units with the same program. Makes it very convenient for the techs, and it improves the accuracy over potentiometers that were not driven and are not very accurate all the time. So that may all sound a little bit complicated, but really it's so very simple. All you have to do is download the ICM Omni app. Now it's so simple. On the Apple devices, you literally lay your phone right over the NFC circle, and it'll automatically take you to the app. You download the app, and you're ready to go. And you then start programming. With the Android, it's a little bit different. You have to go to the Google Play Store and download it. But either way, you get the app on your phone, the ICM Omni app. Then you're going to come up with a screen that says program device. Okay. And then you just select the device that you want. We have several NFC products, but we're going to talk about head pressure control today. So you're going to click head pressure control ICM325A. And then you're going to create a new program. And this will start the process to create your new program. All right, and you'll come up to this screen, which will say edit a program. And you're going to select whether you're using a temperature probe or a pressure probe. And you're going to set that value in probe type. All right. And then you're going to go to the next feature, which is set point. And then you're going to select the set point. That's your pressure or your temperature that you want to maintain. So, for example, when it's a pressure transducer, you can input the pressure that you want to maintain, the head pressure you want to maintain directly here. Now, if it's a temperature, you're going to have to know, based on the refrigerant, you're going to have to know what pressure is related, what temperature is related to the pressure of your refrigerant on your temperature pressure chart for your refrigerant. So let's say you've got R22. R22, if you look up your pressure temperature charts, you want to maintain, you have to know, the HVAC tech would know that they have to maintain for R22 about 225 PSI on the head. So you're going to look at, okay, what temperature correlates to 225 PSI on my temperature pressure chart. That's, you can download from the internet. Most techs will have a handbook with all these things handy. So you look up that temperature pressure chart for R22, you say, okay, at 225, my temperature is going to be somewhere near 80 or 85. So you set your temperature set point to 85. We have preset the ICM325 to match the temperature set point for R410A. R410A wants to be somewhere around 310 to 315 PSI, and in some cases a little bit higher, but typically around 310 to 315. You look at your temperature pressure chart for 410A, it's around 100 degrees Fahrenheit to maintain that pressure. So you set your set point to 100 degrees Fahrenheit. Your hard start, you can adjust from 0.1 to 5 seconds. I generally like to keep this a little bit lower because there's not a lot of hysteresis in this device. So hysteresis is the delay between the turn on time and the time that the fan comes on. So if you make this too high at 5 seconds, let's say, that can cause your fan to come on for 5 seconds, drop your pressure too quickly, shut off the fan, and then the pressure builds back up again. The unit comes back on, but it's going at full speed for 5 seconds, so it drops your pressure really low again, and you can act like a fan cycling control. We don't want that. So if you keep that hard start down a little bit, maybe 1-2 seconds at the most for temperature probes, I usually have to keep it down to 1 second or so for pressure transducers, then you just don't get that fan cycling effect, because you're not going to drop the pressure that quickly. And that can be adjusted at any time if we need to change that. Now, the minimum output voltage, I like to refer that as your fine tuning, right? You set your rough in at your set point, right? So that's your rough in set point pressure or temperature to maintain a certain pressure, depending on which probe you're using. And then you use the minimum output voltage to fine tune the control. So when I say fine tune, I mean that is your range of variable speed. So as you go towards 17%, all right, that means you're going to do more modulation, which is going to reduce your fan speed down to 17% of the output. And you're going to be going very slow, which is going to raise your pressure. Now, vice versa, when you go to 48%, that's the least amount of modulation. And that's where you're going to keep your fan speed up a little bit higher. This is going to be a little bit easier on the motor, and it will lower your pressure. So depending on where you are and with your pressure, If you set your set point and you notice that your pressure is a little bit low and you want to increase that pressure, then you're going to adjust your minimum output voltage closer towards the 17% to bring that, slow that fan down and bring that head pressure up. And vice versa, if your pressure is already too high and you want to lower that down, you would go closer to the 48%, and that would bring your pressure down. So you can fine tune it with that minimum output voltage and get your pressure exactly where you want to maintain it. And it'll try to maintain that within a plus or minus 15 to 20 PSI range. Oh, I forgot to mention, go back to the last screen. I forgot to mention, once you've got all your settings all set up, you lay the phone over the antenna that's on the ICM Omni, which is that pen with the circle around it. You literally press program device if it's an Apple phone, and it will give you a check mark, and it'll say something like program confirmed, or it'll have a note saying that it took the program. And when you see that check mark and it confirms that the program has been set, then you know that your program is in there and you can turn on your unit. Always make sure you do all your programming with the power off. Remember that we're doing near field communication. So we have electromagnetic fields that are created around wires when the power is turned on. Those electromagnetic fields will radiate and interfere with the antenna and the phone and the antenna that's in the ICM control and disrupt that near field communication. So always do your programming with the power off if you can. So let's recap the important operational concepts of this control. It operates as a temperature sensitive motor fan speed control, ensuring sufficient pressure across the expansion valve. Provides full torque to the motor during startup to help ensure that proper fan rotation and lubrication of the bearings. That's your hard start. It's intended to be used with single phase permanent split capacitor motors. Not only intended to be used that way, it has to be used that way. These do not work on electronically commutated motors, EC motors. It will not work with those. It's only for permanent split capacitor motors, which are capable of having their input voltages vary. It's field adjustable, so the user can set the minimum RPM level at which the condenser fan should operate. It has a heat pump bypass feature for heat pumps for full speed operation when you're in heating mode, and applies full voltage to the condenser fan motor under normal conditions for a heat pump, meaning AC conditions whenever full voltage is needed. So for example, when it gets really hot outside and the pressure goes way up, you're not going to want to use variable speed control at all. So it just goes right into full speed above a certain range of temperature or pressure on the condenser coil or system. All right, so remember that all this information will be available in our media library. You can get application guides, product details, sell sheets, cross-references, all from our website at ICMcontrols.com. Do not forget that technical support number will have to be changed. We got a new phone system now. So it'll be 315. That's our maybe the main line or something, but it'll be 1-800-365-5525. That's 1-800-365-5525 or info@icmcontrols.com. We'll get you to our technical support to reach me or others in my department that can help you with any questions that you have. And that concludes our webinar, but I would like to open the floor now to any questions that anybody has on any of the topics that we covered, including wiring, including any of these things that we covered. Concept. Does everybody understand the concept of the control? Why we need head pressure control? where it's used, cell towers, refrigeration, all these different applications, why we need it, where it's used, what's the advantages of the ICM control. Remember, you got air-field communication, you got universal control application, you've got manufactured in the USA. You've got easy stocking capabilities. We can turn around product because it's made here in our plant. A lot of value-added features of the ICM. Universal input voltage, universal control voltage, universal reversing valve. So it's great for both HVAC and refrigeration purposes.
Henry's from Stephen Landry.
Yes, Stephen, what would we have?
Yeah, two things. I remember installing this in California in, I want to say the late 80s, very early 90s, probably when the device was brand new. Today, I use it extensively in grow rooms, like you speak to grow houses. So I work exclusively in the cannabis industry nationally, and I teach people to use it. I spec it in design work, and a lot of people in the industry that work in cannabis also already use it because it, to me, it is the best way to control head pressure in low ambient. And we need it, just like what you're saying. We don't want pressure going up and down. We need a constant process because what we do in a grow room is more like commercial refrigeration than comfort cooling for sure.
Well, I thank you very much for that, because that is a market that maybe not all of our sales reps really know that this is being used in, and it is widely used now in this. And I've got many calls from grow rooms, grow houses that use these very, very frequently. They're a lower cost option to like a BFD. So definitely.
Yeah,
Thank
I
you very much.
wanted to add that I originally just used the temperature probe, but in the last couple of years, I switched to the pressure, and it's definitely the superior way to use this control. I'm even though it does, like you say, using the probe eliminates a leak potential, but using the sensor gives us more precision.
Good. And yourself?
Doing well.
Good, good.
Can you please mute yourself? You're on a different call.
It's not getting back to you yet. Just been trying to catch up on things after
Do you have any
Matt's
other questions?
and Thanksgiving, but
Whoever's on the call, please mute yourself.
advanced over.
Do we have any other questions? And that was a great question, Steve. Thank you very much. Any other questions on application? Any other questions on the wiring? Does everybody understand? Basically, all we're doing with the wiring is we got L1 and L2 going to our control. We're breaking one leg of that power through the control to our fan motor so that we can modulate that voltage on that leg to the fan motor. One leg is held constant on line 1. Line 2 is broken through line 2 and motor 2, so we can vary or phase control that leg of power to the motor. What phase control means is we just change the wave shape a little bit so that we can lower the voltage going to home. Okay. Does everybody understand that? And then the fact that with heat pumps, remember that you can't go directly to the motor. You got to go through the little defrost port relay. That defrost port relay input, usually called DF1 or ODF1. You got to, break that power to ODF1. Take the power leg from the contactor, go to line 2, take the motor 2 output, go back to the relay, so that when that relay needs to open up and defrost and shut the fan motor off, it can do so. And then when we go back to normal operation and cooling mode, we can vary the voltage through the relay to the fan. That's the difference in the heat pump application. And then keep in mind, with the heat pump application, we're defaulted to heat active reversing valve. So if you have a cool active reversing valve, which many people do have, you just place the jumper at the HPO input, enable input, and then wire your reversing valve, wire leads parallel with your bow and your common on your defrost board right to the heat pump terminals on the ICM controls. And that's there so that we know when your reversing valve is active, and that's how we know whether you're in cooling or in heating. And then when you are in heating, we can bypass the control and just run the fan at full speed. I hope everybody has got that concept. If there are any questions, please speak now. You also, any other questions, you may email them to info@icmcontrols.com or reach out at 1-800-365-5525. And we will answer any other further questions that you have. This webinar will be up on our media library and our website after the presentation or shortly thereafter for your availability. And I thank you very much, all of you, for taking some time out today. Again, I'm here for any questions that you have. Don't have any other further questions. This will conclude our webinar today.
Thank you for being here.
Thanks, John.